Hi. Okay, so today we are going to talk about Taylor polynomials and approximations. Well, what is a Taylor polynomial? Taylor polynomial is just a polynomial function that can be used to approximate other elementary functions like sine, e to the x, ln of x. Why would we actually want to do that? Well, back before we had calculators and when calculus was being developed, using like sine of x, e to the x, ln of x, and those kinds of curves and trying to find information about them and discover that was incredibly difficult. But as you know, a polynomial, something like x squared plus 2x plus 1 or whatever, that's much easier to manipulate in terms of differentiation and integration and even limits than sine, e to the x, and ln of x, those types of functions. So Taylor polynomials were developed to create an approximation of these functions, something that's so close, a polynomial function that's so close to these functions and others like them, that your answer will almost be identical to it, like the differentiation or the integration or whatever you're trying to find. So let's actually do some examples here and hopefully you can see them. If you remember the video that I had you watch at the beginning of this unit, this is what Taylor polynomials are and where they're kind of coming into play. So, want to find the equation of the tangent line for f of x equals sine of x at x equals 0, then use it to approximate sine of 0.2. Is this an over or under approximation of sine of 0.2? Okay, well, we've done this like a billion times, right? So we want to find equation of the tangent line. So f of x equals sine of x. F of x equals sine of x, and we need to find our derivative, so f prime of x is equal to cosine of x, and we know that we need to have a point, right? So f of 0 equals sine of 0, which equals 0, so we have the point 0, 0, and then we need to find our derivative at that point. Cosine of 0 is equal to 1, so we can actually write our equation of the line. Y minus 0 is equal to 1 times x minus 0. And I can rewrite this as like y equals 0 plus x, right? Or y equals x. And this actually is a Taylor polynomial. But let's do a graph here. So if we graph this, oops, I smudged it as I was doing that. If I graph sine of x, got something like this, right? Whoop. And here's sine of 0, but here would be like 0.2, right? 0.2. And if I want to draw like a tangent line there, I know that I'm going to have a little, it's hard to see, but I'm going to have like a little bit of error there, right? So let's actually say, what is sine of, we're asked is to approximate sine of 0.2. Well, I can use this equation to approximate sine of 0.2. So y is equal to x. So sine of 0.2 is going to be approximately, we're approximating, so you should use an approximation sign, approximately 0.2, okay? Well, let's go to our calculator. What is sine of 0.2? So I'm going to go here, I'm going to type sine of 0.2, 0.2, and I get 1.9, so like sine of 0.2 is equal to 0.19866933308. So this is slightly too big, right? Slightly too big. And we can see that because our tangent line is above the curve there, right? So this little gap here, that's going to be a little bit too big. But we still have actually written a Taylor polynomial and used it to approximate. And you can see this number is actually really close to the actual. I'm sorry, I pointed the wrong one. This number is very close to the actual here. So our approximation is pretty accurate. So using Taylor polynomials back when calculus was being developed was a really, really good idea. Okay, let's go back to our calculator here. On our calculator, we're asked to graph y sub 1 equals sine of x, so sine of x, and we're going to use the window -9 to 9, and y will be -4 to 4. And then in y2, okay, so like graph sine of x. So you've seen sine of x before. That's nice looking, isn't it? Okay, so let's go to y sub 2, and we're going to graph this. X minus, I'm going to just type this in. You don't have to watch me do it. Okay, I didn't make you watch me do this, but I've typed it in, and I'm going to graph it. Oh, okay. And we're getting a function here. And you can see that this like 7th degree polynomial kind of curves our sine curve there, right? Right? It curves the sine curve there. So we were also asked to add each term, okay? So let's do that. We're going to go back in here. And we've got a pattern going, so minus, plus, minus, plus. So we've got minus, let's do this, plus x to the 9th. Oops, why did I do that? Delete x to the 9th divided by 9 factorial. Okay, and if I graph that, okay, so there's our sine curve. And now we've got a polynomial that looks like, still going pretty slowly, but it's getting there. And that hugs even closer to the sine curve. That's even more accurate. And if I do another term, plus, minus, plus, minus, okay, so I've got x to the 11th divided by 11 factorial. If I graph that, there's my sine curve again. And we're graphing. Oh, it moves so slow, but like it's kind of cool to see it actually do it. Okay, and that's even closer. Can you see that? That's even closer than what we had before. So, what do we notice? Well, we're noticing that they're closer and closer and closer. What's y sub 1 of 0? Well, let's trace it. Y sub 1 of x at 0 is equal to 0. Y sub 2 at 0 is equal to 0. What's it at 0.2? So let's go. Y at 0.2, we've got 1.98. Hey, is it paused? Yeah, okay. So at 0.2, we've got 1.9866933. And at this, at 0.2, we've got 1.9866933. Gosh, that was so close. Was this almost even exactly the same? 866,933? 866, yeah, exactly the same. Now, we know that these lines are not actually exactly the same, right? But our calculator cuts this number off. So, of course, if it goes on, we know that it's going to be different at some point in time. But you can see how this polynomial approximates our sine curve really, really well and really, really accurately. So let's move on here and define what these are. So an nth degree Taylor polynomial. If f has n derivatives at x equals c, then the polynomial p sub n of x is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus da-da-da-da-da f to the n of c times n over n factorial times x minus c to the n power. That's called the nth degree Taylor polynomial centered at c. So c is the center, and this right here, f to the n power of c times n factorial, that's the coefficient of this x minus c to the n term. Okay, that's our coefficient. Now, we do have a slight difference you're going to see possibly on your exam between a Taylor and a Maclaurin polynomial. What's the difference between a Taylor and a Maclaurin polynomial? Well, a Taylor polynomial is centered at c, and a Maclaurin polynomial is centered at 0. So, that's it. That's the only difference. If c equals 0, then this, that's a 0 there, is called the nth degree Maclaurin polynomial for f, and the only difference here is that rather than being centered at c, we're centered at 0. Okay, so let's do an example here. We're asked to find the Maclaurin polynomial of degree n equals 5 for f of x equals sine of x. Then use p sub 5 of x to approximate the value of sine of 0.1 using correct notation. Find the error for our approximation and determine an interval in which sine of 0.1 could actually live. Finally, compare our approximation to the actual value of sine of 0.1. Is it in our interval? Okay, let's do this. Well, if it's a Maclaurin polynomial, then it's centered at 0. So c is centered at 0. And let's, we need to actually have what our coefficients are. So f of x is equal to sine of x. F prime of x is cosine x. F double prime of x is negative sine of x. F triple prime of x is negative cosine of x. F to the fourth of x is equal to sine of x, the fourth derivative. And the fifth derivative of x is cosine of x. Okay, and now since we're centering this at 0, we need to know what like 0 or like f, oops, not what I wanted. We need to say what these are, so we need f of 0 is of course equal to 0. F prime of 0 is equal to 1. F double prime of 0 is equal to 0. Triple prime of 0 is negative 1. 1 second. Fourth derivative of 0, 0. Fifth derivative of 0 is 1. Okay? So these, right here, these are the numerators for the coefficients. Okay? All right, so let's actually write down our approximation. So sine of x is approximately, right? Because we're using p sub 5 of x to approximate this. So is approximately p sub 5 of x, which is equal to, okay? So first we put our f of 0. F of 0 is 0 plus f prime of 0 times x, so that's 1 times x, plus f double prime of 0, which is 0 over 2 factorial times x squared, plus, I'm writing down here because I'm running out of room, negative 1 over 3 factorial times x cubed, plus 0 over 4 factorial times x to the fourth. Did I miss one? Yep, negative 1, 0, 1, plus 1 over 5 factorial times x to the fifth. Okay, and we can simplify this out a little bit. So that's going to be equal to, this is this trash, so it's going to be equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Okay, so that's our approximation of sine. This is what p sub 5 of x is equal to. And now we can use this to approximate sine of 0.1. So sine of 0.1 is approximately, and I'm going to rewrite this out, 0.1 minus 0.1 cubed over 3 factorial plus 0.1 to the fifth over 5 factorial. I'm going to put that in my calculator, but I'm not going to make you watch me do it. Okay, I've entered this in my calculator, and I get 0.998334167. Well, now let's find out what sine of 0.1 actually is. So sine of 0.1 is equal to 0.998334166. Oh my gosh, this is actually so incredibly close to one another. It took that last digit to finally show what the difference is there, right? Otherwise, they're completely the same. That's incredible. Okay, so I think that's enough on that problem there. We compared it to the actual. Is it in our interval? Well, we don't have to actually worry about that right now, but let's move on to another problem. Find the Taylor polynomial of degree n equals 6 for f of x equals ln of x at c equals 1. Then use the p sub 6 to approximate the value of ln of 0, or of 1.1, excuse me. Okay, let's do this again. So f of x is equal, I'm going to make sure we note here that c is equal to 1. So f of x is equal to the natural log of x. Prime of x, 1 over x. F double prime of x is equal to negative x to the negative 2. And I'm going to leave it like this. Oops, x to the negative 1, because it'll be easier to take those derivatives. All right, so then we've got 2x to the negative 3, negative 6x to the negative 4, 24x to the negative 5, And our sixth derivative, negative 120x to the negative 6. Okay, so now we need to, since it's centered at 1, we need to actually find f of 1 and then all those derivatives of 1. So f of 1, natural log of 1 is 0. F prime of 1 is 1. Double prime of 1 is negative 1. Triple prime of 1 is 2. Fourth derivative is negative 6. Fifth derivative is 24. Sixth derivative is negative 120. Okay, cool. So now we've got that, so we can actually approximate ln of x here. So ln of x, we can write out our Taylor polynomial. How is a Taylor different from a Maclaurin? Well, they're the same, but Maclaurin's centered at 0. So ln of x is approximately p sub 6 of x, which is equal to, okay, 0 plus 1 times x minus 1 plus negative 1 over 2 factorial times x minus 1 squared plus 2 over 3 factorial times x minus 1 cubed minus 6 over 4 factorial times x minus 1 to the 4th plus 24 over 5 factorial times x minus 1 to the 5th minus 120 over 6 factorial times x minus 1 to the 6th. Okay? Woo, that is ugly. But we could use it anyway to approximate ln of x. So let's actually do this. If we use this and we approximate ln of 1.1, it's approximately p sub 6 of 1.1, which is equal to, we're going to have 0.1 plus, So 0 would be just 0. Then 1 times 1 minus 1.1 is 0.1, right? So then we're going to have 0.1 minus 0.1 squared over 2 factorial plus 2 times 0.1 cubed over 3 factorial minus 6 times 0.1 to the 4th over 4 factorial plus 24 times 0.1 to the 5th over 5 factorial minus 120 over, times 0.1 to the 6th over 6 factorial, okay? And if I put all of this in a calculator, I get answer of 0.09531016667. And let me pause here.